Hello, this is the fifth video of a series of videos on linear transformations from Rn to Rm. And we've talked a lot about linear transformations, their mappings from Rn to Rm that satisfy the linearity property. And we've seen that every matrix defines a linear transformation from Rn to Rm, if you have a n by n matrix. And one thing we'll see today is that you can go the other way around, which is whenever you're given a linear transformation from Rn to Rm, there's actually a matrix that will do the transformation, basically. And that's very useful because it basically says that these linear transformations from Rn to Rm are very concrete things. You can actually get a matrix, and then you can understand the transformation by working with the matrix. So let's just write some of that down. So we've seen that every n by n matrix A defines a linear transformation that we call T sub A from Rn to Rm. And what is that linear transformation? It's multiplication by A, given by T sub A of x equals A times x, where x is an element in Rn. And one thing we'll see is that conversely, every linear transformation T from Rn to Rm has an associated matrix. That is, okay, what does that mean? i.e., there is a matrix A such that T of x is equal to A times x. In other words, every linear transformation really from Rn to Rm really can be thought of as a matrix times a vector operation. Matrix vector operation. And so how do we, okay, let's back that statement up, right? What is the matrix A? So what the matrix A is, you take, well, so first of all, I think I introduced these vectors, but if you have E sub 1 through E sub n, these are called the standard basis. Maybe I just didn't give it the name. The standard basis vectors in Rn. Okay, what are these? So EIs, I haven't even defined A yet. We'll define A after I tell you what the standard basis vectors are. Okay, so let's just scan that. Standard basis vectors in Rn is defined by EI is zeros. Okay, but you have a 1 in the ith column. The ith component. So the ith component is 1. Everywhere else is 0. And you have n of these. So for instance, in R2, you have E1 and E2. E1 is just 1, 0. And E2 is 0, 1. Okay, so those are the standard basis vectors. In R3, you get E1, which is 1, 0, 0, E2, which is 0, 1, 0, and E3, which is 0, 0, 1. And you can imagine doing this for any n, right? And, you know, maybe multivariable calculus, you might be used to calling this I hat or I, and then calling this J, and then this one would be I hat, this one would be J hat, and this one would be K hat. Okay, it's the same thing, except just in general, there are E1 through En. Okay. The hat stands for unit vector. Okay? Okay, I don't think I need to do the example of R4. I think you can see what those are going to be. Now, any vector... now we're ready to say what the standard matrix is. Okay, great. Let's define... So now we're ready to give the definition of the standard matrix A. A is going to be called the standard matrix. And what it is... So to tell you what A is... Okay, A is like a matrix, right? A is a matrix. It's just a bunch of numbers. And A has a bunch of columns. And if I tell you what each column is, that will tell you what A is. So that's what I'm going to do. I'm going to tell you what the columns of A are. And the jth column of A is defined to be T. So I have this linear transformation T, and I'm trying to get a matrix A out of it. You plug in E sub j, and that vector that you get, that's defined to be the jth column vector of A. Okay, so in other words, you take T of E1, you make that the first column, you take T of E2, you make that the second column, and you go out to T of En. Now notice that let's check that this is actually an M by N matrix. So obviously we have, how many columns do we have? We have N columns, right? One for each of the EIs. So this is N columns. And how many rows do we have? Well, that's the same as how many components does each of these columns have. And we have a linear transformation T from Rn to Rm, right? So the T of EJs, they're the outputs of the EIs, and so they're going to be vectors in Rm. And so, in fact, A does have M rows. So this is an M by N matrix. And this matrix is called the standard matrix of T. Okay, so you can get this matrix out of T. You just plug in the EIs and you get this matrix, which is called the standard matrix of T. But that's not, by itself, that's not significant, right? Okay, you get this matrix, so what? The point is that we can check, okay, what's the significance of this matrix? What's so special about it? What's special about it is we need that for all x in Rn, okay, T of x, what you get by plugging in x into your transformation T, that's the same as what you get if you do A times x. That's the point of this matrix, right? So you start off with this linear transformation, okay, and then you get this matrix out of it, and you're like, wait a minute, this transformation isn't so mysterious after all. All I'm doing is I'm just taking A and multiplying it by that vector. Like, all I'm doing is applying a matrix to those vectors. That's what you're doing when you have a linear transformation from Rn to Rn. Okay, so let's check that this is in fact true. Well, first of all, let's check that they agree. So first, let's see what happens when x is a standard basis vector. EI. Okay, so is T of EI equal to A times EI? Well, we know that A times EI in general is the ith column of A. Okay, so that's just a general fact about matrix times vector multiplication. Because, okay, maybe I should just do an example just to review why this is true. So if you have some matrix A, okay, let's say you multiply, let's say this A is a 3 by 3 matrix, and you multiply by 0, 1, 0. So that's E2. And you have this matrix A, B, C, D, E, F, G, H, I. Then this is going to be 0. I'm thinking of matrix times a vector as taking combinations of the columns. It's going to be 0 times the first column plus 1 times the second column plus 0 times the third column. And so that's just going to be the second column. So that's just an example of how that works. And in general, it's true that if you have an m by n matrix and you multiply by EI, you just get the ith column of A. Well, the ith column of A, what's the ith column of A? By the way we constructed A, the ith column of A is T of EI. Right? That's how we came up with the matrix A. So this is going to be T of EI. And so therefore, A times EI is in fact equal to T of EI. Okay. Now let's see what happens in general. Now, this is where the linearity comes in. Because we know that every vector x, so let's say that x has components x1 through xn. Every vector x is a linear combination of the EIs. It's x1 e1 plus x2 e2 plus dot 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 plus xn en. So therefore, T of x, okay, T of x is going to be T of x1 e1 plus dot 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 plus xn en. Right? Because that's what x is. Now, since T is a linear transformation, by the linearity of T, how can we write this? This is x1 times T of E1 plus dot 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 plus xn times T of En. Right? We can distribute the T across. That's basically a linear transformation is a transformation T such that you can distribute the T across when you have this linear relationship. Okay, and we established that this is equal, that the T of EIs is equal to A times EI. So this is x1 times A times E1 plus dot 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 plus xn times A times En. Okay. And we know that matrix vector, so now I have a matrix vector multiplication, and this is going to equal A times the vector x1 e1 plus dot 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 plus xn en. Now why is this true? Why are these equal? Because of the linearity of matrix vector multiplication, right? Linearity of the function that takes x to A times x. I know that this is a linear function, so I can distribute the A across. And now now we're ready to see what happens. What is this thing that I'm doing a times? It's x, right? X was this. So this is a times x. So what did we discover? We discovered that t of x is in fact equal to a times x. So let's do an example. Let's say that you have the linear transformation t of x1, x2, x3 equals x1 plus x2, x2 minus x3, 3x1. Okay, what's the standard matrix of t? So we need to figure out, okay, what matrix times x1, x2, x3 will give you this output x1 plus x2, x2 minus x3, 3x1. So let me show you two ways of finding the standard matrix. So one way to do this is, well, we know that by definition A is the matrix whose columns are the t of ei's. So one way to do it is just to calculate the t of ei's and then make those the columns, right? So one way is to find the t of ei's, and so I see that my input has three components, right? So this is a linear transformation whose domain is R3, and what's the codomain? The codomain is also R3 because the output has three components. So I know that I have a 3 by 3 matrix, and so my n is 3. So I have an E1, E2, and E3. So let's plug in t of E1. Let's calculate what that is. That's t of 1, 0, 0, and that's going to be, okay, you just plug that in, you get 1 plus 0 is 1, 0 minus 0 is 0, 3 times 1 is 3. Now let's plug in t of E2, that's t of 0, 1, 0, that's going to give me the point 1, 1, oops, what did I do there? 0, right? And now when I plug in E3, I'm going to get t of 0, 0, 1, and what am I going to get? I'm going to get 0, 0, no, I'm not. I'm going to get 0, negative 1, 0. And so therefore, my A, okay, well, I have the three columns, right? This 1, 0, 3 is my first column, 1, 1, 0 is my second column, third column is 0, negative 1, 0. Now let me make sure I'm recording because sometimes I think I'm recording, but I'm not, and then I just wasted a bunch of time. Okay, so this is my standard matrix. So this linear transformation, okay, when I plug in my x1, x2, x3 vector into T, what I'm really doing is I'm multiplying that vector by this matrix A. So that's one way to find the standard matrix. Let me show you another way. Another way is to sort of like fill in the blanks. So I know that my A is a 3 by 3 matrix by looking at this T. And I know that when I multiply by x1, x2, x3, I have to get x1 plus x2, right? So that's 1x1 plus 1x2 plus 0x3 My second component is 0x1 plus 1x2 minus 1x3, because it's just x2 minus x3. And then my third component is 3x1. Well, 3x1 is 3x1 plus 0x2 plus 0x3. And now you can sort of fill in, I have 9 blanks that I need to fill in, and they're going to be numbers. And when you multiply them by x1, x2, x3, I'm supposed to get this vector. So if I take, let's look at the first row. This row times x1, x2, x3 has to be that. So obviously the numbers have to be 1, 1, and 0 to make that work. And similarly, the second row has to be 0, 1, negative 1. Okay, and then the third row has to be 3, 0, 0. And so that's my matrix A. That's another way of doing it. Okay, let's look at one consequence of this theorem. So before, we've looked at examples of linear transformations and an example where it's not a linear transformation. And now we see that since every linear transformation, from Rn to Rm is given by matrix multiplication, okay, let's say that our matrix of a linear transformation is A, and we have this random matrix A11, A1n, AM1, AMN. Remember, that's our general notation for a matrix. The ij entry is A sub ij. We know that when you multiply such a matrix A by x1 to xn, this vector x, okay, you have to get A11 x1 plus A12 x2 plus dot 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 plus A1n xn. So your x1 to xn are scalars, right? They give you this vector x. And then the second component has to be A21 x1 plus A22 x2 plus dot 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 plus A2n xn. And then you go all the way to AM1 x1 plus AM2 x2 plus dot 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 plus AMN xn. So I know that every linear transformation from Rn to Rm has to have this form. The first component has to be, well, actually all of these components have to be in some sense a linear combination of x1 to xn, where, well, this time x1 to xn are numbers, right? So let's just write that down. So the components of the output are linear combinations of the scalars x1 through xn. And so that shows me why something like, if I have something like t of x1, x2 equals x1 2x2 e to the x1, okay, this is definitely not a linear transformation. So for example, I can see that this is not a linear transformation because this third component, well, it's not a linear transformation, I should say, from R2 to R3, because I can see that this e to the x1 doesn't have the format that the components are supposed to have. Right? This third component, each of these components needs to be a constant times x1 plus a constant times x2. If it's not, then it's not a linear transformation. I know I don't have a linear transformation from R2 to R3. So that's a quick way of seeing when you have a linear transformation and when you don't. If your transformation from Rn to Rm has this form, then it is a linear transformation, otherwise it's not. So yeah, so this is important. And then one more thing I should add is that this is only for linear transformations from Rn to Rm, this standard matrix. Okay, where is it? Yes, from Rn to Rm. And one thing we'll hopefully learn about is linear transformations from one subspace of Rn to another subspace. Okay, so linear transformation is a more general concept. Linear transformations don't have to always have the domain be Rn and then the codomain is Rm. They can have different domains and codomains. Now when you have such a linear transformation, which we haven't talked about yet, but hopefully we will, when you have such a linear transformation, there will not be a standard matrix of that linear transformation. So this relationship between linear transformations and matrices, that's only for linear transformations where the domain is Rn and the codomain is Rm. So, sometimes I've watched these videos on linear algebra where they say, well, matrix multiplication is the same as linear transformations. Okay, that's not actually true. That's only for a specific type of linear transformation. So what that means is that linear transformations are actually more general than just matrix multiplication. Okay, so here's like a little diagram. So here's matrix. Here are matrices, the matrix vector multiplication. And then this you can think of as linear transformations from Rn to Rm. But then you have all these other linear transformations. So here is all of the linear transformations. Okay. And the one that we have been looking at is only the ones here, where the domain is Rn and the codomain is Rm. But the linear transformation concept is way more general. There's way more linear transformations that we haven't even talked about. And to understand these general linear transformations, they're functions, they're mappings from one vector space to another. So V and W are called vector spaces. And in this series of lectures, we won't talk about vector spaces. So this is the first course in linear algebra. We won't talk about vector spaces, but you should know that there's things called vector spaces. And Rn and Rm are examples of vector spaces. Actually, we'll talk about subspaces of Rn, and subspaces are also vector spaces. But there are a lot of vector spaces. So there's lots of linear transformations. So that's just what I want you to know. That sometimes people will say, well, linear transformation is the same as matrices. That's not really true. That's only when you're looking at this blue part of the diagram. Okay, so that's linear transformations and the standard matrix. In the next video, we'll talk about one-to-one and onto. Those are general notions of functions, and we'll see how they're related. We'll bring back the echelon form, the linear independence, and how that all ties together. Thanks for watching.